So today we are discussing about Unit 17. Unit 17. Unit 17. Bounded linear functionals. Bounded linear functionals. Bounded linear functionals on LP mu. LP mu. So contents, what are their contents? Aims and objectives. Introduction. Bounded linear functionals or LP mu. Reach representation theorem. Hmm? Aims and objectives. Suppose L is a normal linear space over K is where K is a real or complex set. A mapping F from L into K is called a linear functional on L. If alpha x plus beta y equal to alpha f of x plus beta f of y for all x comma y belongs to L and alpha comma beta belongs to K. In this unit, we characterize the bounded linear functions on the normal linear space LP mu. After completing this unit, you will be able to identify the structure of the bounded linear functionals on LP mu as given in the Ries representation theorem. Introduction. Suppose L is a normal linear space. So over K equal to either real number set or complex number set. Real set, complex number set. A mapping of L to K is said to be linear functional. Said to be linear functional. Concepts. Concepts. Concept. Linear function. X comma y belongs to L and alpha comma belongs to beta belongs to K. We have f of alpha x plus beta y that equal to alpha f of x plus beta f of y. Defining the boundedness of a linear functional on normal linear space, we give a class of linear functionals on LP mu in section 17.3 and prove that each one of them is bounded in section. So we characterize all bounded linear functionals in LP mu. Bounded linear functionals on LP mu. So definition. 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 Suppose L is a normal linear space over K. Suppose. SP means suppose. L is a normal linear space over K. Linear space over K. Where K is a where K is a real number set or complex number set. Real or complex. Real or complex. Real or complex. Okay. Real or complex. Real or complex set. A linear functional F on L. Linear a linear functional linear functional linear functional F on L F on L a linear functional is said to be bounded is said to be bounded is said to be bounded if there is a constant m greater than 0. There is a constant there is a constant m greater than 0 m greater than 0 such that mod f of x less than or equal to m. St means such that mod f of x less than or equal to m less than or equal to m less than or equal to m. So m of norm x less than or equal to m of norm x. For all x belongs to L, for all x belongs to M, for all x belongs to M, belongs to M. To M. Bounded linear functional on LP mu. This is called bounded linear functional on LP mu. Using this definition to prove one theorem that is Steinmer's theorem number theorem number. Suppose P and Q are non-negative Suppose P and Q are non-negative. The question formation is prove that and show that. Suppose P and Q are non-negative extended real numbers. P and Q are non-negative non-negative extended extended real numbers such that real numbers real numbers such that estimates such that 1 by P plus 1 by Q by P plus 1 by Q 1 by P plus 1 by Q equal to 1 for any G belongs to LP. G belongs to LP. LP LQ and FG define define FG FG LP mu LP mu tends to K tends to K by FGF FG FG EF X FG D mu FG D mu for F belongs to LP mu LP mu. Then prove that. Then prove that. Then prove that. Yeah, FG is bounded linear functional. Yeah. FG is bounded. BDD means bounded linear functional. Linear functional. Bounded linear functional on LP mu. LP mu. B. Norm FG. Norm FG. Norm FG equal to norm G equal to norm G. Norm GQ. Norm GQ. Okay. The proof of theorem. Mm. If F1, F2 belongs to LP mu, if F1, F2 belongs to LP mu, LP mu, and alpha comma and alpha comma beta belongs to K, belongs to K. Then by integral, then by linear integral, linear integral, linear integral, we have Fg alpha F1, alpha F1 plus beta F2, beta F2, that equal to integration x alpha F1, alpha F plus beta F2, beta F, G d mu, G d mu, that equal to alpha F1 G d mu, alpha F1 d mu plus beta integration F2, F2 G with F2 G d mu, that equal to that equal to alpha Fg F1, alpha Fg F1 plus beta Fg F2, Fg F2, F2. Proving that Fg is proving that proving that proving that proving that Fg is a proving that Fg proving that is a linear functional on is a linear functional on linear functional on Fg Fg. Fg. We consider different cases. we con- we consider different cases. Different cases. Different cases. Different cases. Case one. Case one. Yes. Suppose P equal to 1. Suppose P equal to 1 and Q equal to infinity and Q equal to infinity. Finite. Then G belongs to L infinite mu. Then G belongs to mu. L infinity mu. L infinity mu. And for any F belongs to L1 mu. We have FG. We have FGF. FGF. FGF equal to integration FG d mu. FG d mu. Now by Holder's inequality, by Holder's inequality, inequality, Holder's inequality, FGF, 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 that equal to integration FG d mu, integration FG d mu, FG d mu is less than or equal to norm F1 less than or equal to norm F1, norm G, norm G, infinity, that equal to M, norm, norm F1, norm F1, where M equal to, where M equal to, where M equal to norm G infinity, norm G infinity, so that FG is, so that, so that FG is, FG is bounded linear functional, is bounded linear functional, bounded linear functional, bounded linear functional, bounded linear functional. So case two, there are three cases. Case 2. Suppose P equal to infinity so that Q equal to 1. Suppose P equal to infinity and Q equal to Q equal to 1. Q equal to 1. Then G belongs to L dash mu. Then G belongs to G belongs to L dash mu. G belongs to L dash mu. And for any F belongs to any F belongs to F belongs to F belongs to L mu L mu L infinity mu L mu infinity L infinity mu we F G F G F G F F G F equal to integration equal to X F G D mu X F G D mu D mu again by Holder's inequality again by Holder's inequality by Holder's inequality inequality Holder's inequality mod F G of mod of F G F F G F F that equal to integration X F G D mu F G D mu mu is less than or equal to norm F infinity into norm G 1 that equal to 1 that equal to M norm M into norm M infinity, where M equal to norm G1, where M equal to norm of norm G1, norm G1, norm G infinity, norm G1, norm G1, showing Fg is bounded, showing Fg is bounded, script F is bounded. Case 3. Third case. Suppose T lies between 1 to infinity. Suppose T lies between 1 to infinity. Next, G belongs to LQ mu. G belongs to LQ mu. LQ mu. For any F belongs to LP mu. For any F belongs to LP mu. LP mu. We have FGF. We have FGF. FG. F equal to FG d mu integration X. FG d mu. By Holder's inequality, we get by Holder's inequality. Inequality. We get Holder's inequality. We get Holder's inequality. We get Fg belongs to L dash mu. And norm Fg1 and norm Fg1 norm Fg1 less than or equal to norm P, norm Q, norm GQ, Fg, Fg1 is less than or equal to norm Fg, norm Fp into norm GQ, norm GQ, norm GQ, which gives which gives which gives mod FGF, mod FGF, mod FGF that equal to mod integration Fg d mu integration Fg d mu that equal to norm Fg1 Fg1 less than or equal to less. norm Fp norm GQ norm GQ showing that Fg is bounded linear functional, showing that Fg is Fg is Fg is this is first case. Proof. This is A bit proof. Showing that Fg is bounded. Showing that Fg is bounded linear functional. BDD means bounded linear functional. First bit proof. Second bit proof. It is sufficient to show that is sufficient to show that F circle belongs to LP mu. There is F circle belongs to LP mu such that norm Fg F circle equal to norm F circle P circle G norm Q. Suppose G belongs to suppose G belongs to LQ mu is given, we write F circle equal P Q by P Q by P. So SGN means signum of G. SGN G means signum of SGN signum of G. Next, here SGN A, where SGN A that equal to 1, 0 or -1 according as A greater than 0. According as A greater than 0. A equal to 0. A equal to 0 or A less than 0. A less than 0. Equal to 0 or A less than 0. Then we have mod F naught P equal to mod G Q, so that integration F naught P d mu mod F naught P d mu equal to integration x GQ d mu GQ d mu d mu d mu. So less than infinity, showing that F naught belongs to LP mu and norm F naught equal to norm G P to Q. G also FG F naught F naught F of F naught equal to integration x F naught G circle G d mu that equal to G mod G Q by P SGN means signum G d mu, that equal to integration x G S G and G S G and G S G and G mod G Q by P mod G Q by P Q by P d mu, that equal to norm G whole power Q, that equal to norm F naught P, that equal to norm F naught into norm not P into norm F naught P to P minus 1, P minus 1, that equal to norm F naught P, that equal to norm C naught G Q, norm G Q. Since G belongs to LQ mu, G belongs to LQ mu, where is the F naught belongs to LQ mu? LQ mu, LP mu, which norm F naught norm G Q, showing norm FG, norm FG equal to norm GQ, norm GQ, hence proved, hence proved. So one more theorem, that is weak representation theorem. Weak representation theorem. So theorem raise representation theorem, RIESZ raise representation theorem. Oh, statement. Suppose XA is a measurable space, comma J, measurable space, measurable space, measurable space. Mu is a finite measure of X. Mu is a finite measure of X. Finite measure of X. And F is a bounded linear functional. F is a bounded linear functional. Bounded linear functional on LP mu. LP mu. Then there exists a unique element. G belongs to LP, LQ mu, such that, F of F, F of F equal to XFG d mu, XFG d mu. Such that. Then there exists, prove that from here. First, it will come prove that or show that. Then show that, such that. Then there exists a G branch. Prove that G branch. That means, that means Proof of representation theorem. Proof. Yeah. Suppose X is a measurable space. mu is a finite measure X. Suppose X comma here is X comma A is measurable space. Measurable space. Measurable. Mu is a finite measure on X. Is a finite measure on X. Measure on X. Finite measure on X. Finite measure on X. Finite measure on X. First, we prove that G belongs to LQ mu. LQ mu. LQ mu. Let G1, G2 be functionals. Let G1 and G2 be functionals. Functionals. Functionals such that FG of FG of FG of equal to FG of equal to X FG 1 D mu FG 1 D mu that equal to integration X FG2 mu FG2 mu. Equation number 1 star. Equation number star. For a very F belongs to a very F belongs to LP mu. Since integration X XX P D mu P D mu D mu that equal to mu of X less than infinity the hypothesis. So that star gives Not use integration x capital X small x g1 d that equals integration xx x g2 d mu dt d mu. That is integration x g1 d mu integration g2 d mu showing g1 equal to g2 ae means almost everywhere. G1 equal to 0 LPQ moving in this one. So case 1. Case 1. Case 1. P is greater than 0. P is greater than 0. Using the bounded linear function, f is defined as f is defined on LP mu, LP mu, on LP mu. We shall define a set functional lambda functional lambda on A by lambda equal to lambda equal to fxa fxa. Okay. Rod E belongs to here. The claim lambda is sign major and A is absolute continuous with respect to mu. First of all, if A and B are disjoints here and X A union B equal to X of A union B equal to X of A union B equal to XA plus XB. X of A plus X of B. X of A. So that by linear of F, so that by linear of F, linear of F, we get lambda of A union B, that equal to lambda of A plus lambda of B lambda of A plus lambda of B. Here, therefore, lambda of, so lambda of E equal to limit n tends to infinity, n tends to infinity. Lambda of union equal to 1 to n, equal to 1 to n. EI, that equal to sigma n equal to 1 to infinity, 1 to infinity, lambda En, lambda En. So lambda of E equal to, therefore, by Radan-Nikodym theorem, therefore, by Radan, Radan, Nikodym theorem, theorem. So lambda of E equal to, lambda of E equal to integration E G d mu, G d mu for all E belongs to A, belongs to script A. So equation number 1. Now we now show that G satisfies condition of the theorem, that is R of F equal to F of F equal to F of F equal to integration X G of d mu, G of d mu for all F belongs to LP mu. Equation number 2. So norm, that means norm of F, norm of F equal to norm G Q. This is equation number 3. Equation number 3. Now prove that, note that Holder's inequality gives by Holder's inequality gives Holder's inequality gives mod F of F, mod F of F less than or equal to norm FP, norm FP FP to norm GQ, norm GQ. So that norm F norm F less than or equal to norm G, norm G, Q, equation number 4, equation number 4. That is, that is, that is mod GQ d mu GQ GQ d mu d mu less than or equal to norm F G, norm F, norm F Q, Q. Since XEN, XEN tends to 1, as n tends to infinity, as n tends to infinity, showing G belongs to 1. Showing G belongs to LQ mu and norm G Q less than or equal to norm F Q R norm G Q less than or equal to norm F. Equation number 5. So case 2. Case 2 homework. Case 2 homework. Good. Okay. Today we will discuss two theorems. One is Ries representation theorem, most important for 10 marks theory, and first theorem, theorem 1 and theorem 2. Okay. So this you do attach homework. Okay. I'm leaving meeting. Thank you very much.